Hello, good afternoon. Oh, my voice is very strong here. Is it good for you? Is it? Yeah, okay. Good afternoon. First of all, thank you for the invitation. I think Victor is still not here. Thank you, Victor, as well. Very nice to be here in person. I will be talking, I'm Elias. I'm a director of the Causal AI Lab at Columbia. I will be talking about causal data science general framework for inference and fusion. If you're on Twitter, follow me there. If you want to have some kind of heated discussion sometimes on AI, general AI, causal inference, and so I'm usually there. Happy to be here. Idea of the talk is try to share part of the research program that I'm developing maybe in the last decade almost. And I'll do a little bit of a survey. I'll start with the big picture about what's going on in the field. Then I'll try to be a little bit more concrete, and then I'll disconnect again and make the kind of the broader, in the broader sense, what we are doing. My goal is not also to discuss the technical details. Of course, I will just kind of I'm trying to introduce the tasks and the kind of problems and the kind of way of thinking about some of the issues, at least the way that I like to think about. I should also add, even after our conversation earlier, my bias will be try to understand these problems in causality that is it cut across so many different areas, and I will kind of do it from the computer science perspective through computational lenses, given that this is my bias. I'd like to start with some kind of aspirations and challenges from some of the thinkers of our generation about modern data science, starting with Professor Hal Variant, chief economist at Google, and Professor Tusser Berkeley. They said that data science is about ability to take data, to understand it, to extract value to it, to communicate it. That's going to be hugely important in the next decades. And he goes on to say that like computer or programming or coding is kind of trickling down, and even people now in the high school start trying to do that or doing that. Now we also have this in with the data science skills to be discussed what this exactly means. Hopefully this will be the case here today. Now, the Professor Gary King of political science at Harvard and statistics at Harvard saying big data or data science, I would say, is not really about the data, which is an interesting quote. And then we have also Professor Yuda Pro at CS, Computer Science and Statistics at UCLA, saying data science is only as much as a science as it facilitates the interpretation of data, a two-body problem connecting data to reality. And interesting here that, and there are wisdom here across the spectrum. And it's nice to see also many disciplines kind of engage in the discussion about what is this thing that we call data science. This is a data science series. The first one is saying that it's all about, in some way, is all about the data. The second one say it's not really the data, or say, let me pose in this way. And the third one says data plus X. It's data and combination and something else. Hey, Victor. Then we like to kind of try to unpack that. I'll add also from Professor Ioannidis, professor in the medical school at Stanford, saying that why most published research findings are false. And I think it's very, my spin can go to the paper and he has his own theory and the way that he explains that. I'll try to give a little bit of this feeling from the causal perspective. I don't think that his statement is false. I think that his statement is true. Then, and the question now is, why is this happening? And sometimes the best and the brightest are engaged in this type of research, and there is this general feeling that the results are really not robust, and you kind of change a little bit. Sometimes you cannot replicate. Many times the replication crisis. Sometimes you just change a little bit, and things already break down very easily. That you don't have any kind of robustness, and this is pretty not good. Then the question is why this is happening. Now, our goal is to understand that. Again, I will do from the lenses of computer science and my causal lenses, or causal lens. And the general goal here would be to, in order to understand that and maybe solve the problem, first understand and then solve, the agenda here is try to develop a causal inference engine, which from the computer science perspective include languages, algorithms, and some types of guarantees for performing data fusion about population-level interventions by cohesively combining multiple heterogeneous data set. This is based, or at least a survey from what was going on around 2016 or 15, this procedure of the National Academy paper with Yuda himself, that's called Causal Inference and the Data Fusion Problem. Another reference here of what I talked today. Also, there is this paper that is just appearing now. It was submitted in 2020. That's called Pearl Hierarchy and the Foundations of Causal Inference. That is very related to the ladder of causation. If you heard about, this will kind of guide in some way our thoughts, and it will be an important tool for us. If you haven't checked the book called The Book of Why, take a look. I think it's an important motivator and inspirator to understand, inspiration for understanding why we are today. Coming back here to reality, data, everyone is very excited about that, me included. I think the challenge here, as we posted in this PNAS paper, all data is not created equal. What do we mean here? The observation that there is a lot of data out there, but this data is almost invariably collected under different experimental conditions. The underlying populations are not the same. The sampling procedure, how we draw samples from the population, is not randomized, as usual, the usual assumption. The treatment assignment, or the exposure, is not randomized. And many variables are not measured, or not measured consistently across the data sets. In other words, it's almost like let's cry together here. In other words, the collected data is really messy, and very rarely matches the inferential target. Inferential target is the kind of statement that we are trying to make. Important point here, I wanted to write that because there is a lot of some people saying that the theory is about when the situations are not perfect. The whole goal and motivation to have any type of causal inference theory is like things are not going as expected, or they don't match this inferential target. The joke is like we can put a bunch of monkeys typing, and if things are matching the inferential target, they will eventually converge, and you get the right answer. Here, you need something else in order to solve the problem, and the very reason for existing any type of causal inference theory seems very kind of gloomy type of scenario. The positive here is that, and we like to explore, is that all these dimensions are now formalized. Each one of them. I'll go one by one. And also, once this is formalized, then you have a data set that is in this kind of 4D space here, or 5D space. Each data set is one point related to one instantiation of this thing, of these dimensions. Then we'll try, and you have the target, and you will try to understand when you can move from where you collected to where we're trying to go, or the type of statement that we're trying to make. Now, again, dimensions formalized, and also what I mean is like there are conditions and algorithms to decide what is entailed from a certain, what can be inferred from a certain data collection. Now let me give a little bit more, somewhat concrete example. Suppose that we have the inferential target that we're chasing here, that is the quantity Q, that is equal to P star of Y given to X, some effect of some intervention. You can also write in the Y sub X alternative notation for this particular quantity. I think people may be familiar here in the room. This is in contrast with this P star of Y given X. We don't want to just train a classifier or have the conditional probability of Y given X if you're trying to do the prediction. You want the effect if you do the intervention on X on Y. Now, we have these different data sets that are common, data set 1, 2, and N. That's good. Now, I'll go dimension to dimension as promised. First dimension, I say the underlying populations are not the same. Perhaps the first data set that we have is coming from New York. You have a different data set in Boston. You have a data set in Texas. Not the same. Maybe there is a different type of ethnic, cultural, genetic compositions from the data that you collected in Texas. Maybe there's a little skew towards the Spanish type of representation than what we have in New York, for example. That's all good. The question needs to account for that. The populations are not the same. This is dimension number 1. I'll repeat that a few times. Dimension number 2, the way that you submitted the population to the exposure are not the same. There is some kind of confounding in the treatment assignment. For example, here in the population that is coming from Boston, the data is observational. On the other hand, the data that is coming from Texas is experimental. We did have some controllability power there, or interventional power. Very importantly, usually it's just experiment or not for us. Here, we are able to control the variable Z2. could be maybe the diet of the person, but our inferential target was the X. We are trying to get the cholesterol. What's the effect of X? Could be the cholesterol in Y, that is heart failure. We are unable to randomize cholesterol in the population in Texas, but you are able to cholesterol Z2, that is diet. Maybe here we are able to do Z1, that is the exercise that the people are doing. Then there's no match here. Inferential target is very different than what the data you collected. This is dimension number 2. What is the experimental condition? Dimension number 3, maybe there is some kind of selective pressure over age here. In the data that is coming from New York, we are collecting samples that is from landlines that we are calling people. Maybe there is an overrepresentation of older people. No one with more than 40 years old, or sorry, less than 40 or even 30 maybe, they don't have a landline. Then we are kind of skewed towards certain population. And the variables are not measured consistently. You don't across data sets. Then sometimes this is a time series. You measure X1 here, but you don't measure the second shot of the drug or the decision X2, while here they have both X1 and X2. That's good, but not the same columns in the data set if you want the syntactic description of what's happening. Then this is like kind of heterogeneous in this sense. It's an overloaded word. But anyhow, this is what we like to formalize or to leverage. Keeping that in mind, now I would like to discuss the different tasks that we have as a function of these dimensions. Starting from the task, of there's some common tasks. Let me read it. In scientific circles, AI, machine learning, and the statistics, assumptions. First one that we have, and I will go fast here, but the first one that we have is big deal, descriptive statistics. This is my reading of history, I should say. Then you can cut differently. But what was the challenge there? You are getting from something very specific and finite in general to something that is unobserved and abstraction that is from samples to the distribution of the observational distribution in this case. Then what I mean by it took maybe 100 years or 200 years to us to understand how to do this inferential step from the sample that is the specific to the most general one. A lot of discussion in the science of philosophy of science about problem of induction. But anyhow, this is one first building block here for our data science as a discipline. Second block, that is another revolution, took a good amount of time, was about now there is the idea of another kind of distribution, another beast here in the zoo or animal in the zoo, that is the do distribution, the intervention of the causal distribution. Then Fisher has this idea, I consider one of the biggest discoveries of the previous century, having the randomization the way that he did of the assignment of the drug in the case of a farm. It was the agriculture was the high tech at the time. But we are still going from sample to distribution, but this is special distribution now that we are able to assess through a physical procedure that is Fisher randomization. Now there is a new element here, or a new animal in the zoo, and why the big fuss, that is called causal inference. I would like to qualify that as causal inference from observational studies. And the type of inference that we are trying to do there, at least in the prototypical way, is not about the samples, but we are moving across distributions here, from the observational distribution to the experimental distribution. New kind of inference. How do you do that? We could see as being from this across these guys here also, kind of combining. Once we quote unquote solve, and don't get unhappy here, it's a hard problem. But at least at some level, you understand how to do this step. Now we are with this distribution. Maybe I have 0 samples from this one. How do I get this other one here? Then this is called causal inference from observation study. Again, my reading of history, causal inference from 1974 until 2011 was mainly concerned with confounding bias. Confounding bias is the difference between the two distributions. The do distribution and the C, the observation distribution, or the C distribution. Was concerned with confounding. And has been essentially solved, at least in principle. We understand what does it take by Rubin, Robbins, David, and Pearl. Those are some of the people. There are many people involved in this journey. It's a kind of generational effort that happened for, I don't know, more than 30 years to understand this arrow here. And that's good. Again, in practice, very hard. Don't take me wrong here, unless someone will start shooting or be very unhappy. In practice, super hard. In principle, we do understand it. That's good. Now, question here is like, Elias, are you saying that you are done? Because this sounds a very pretty and cute picture. Seems many good stuff. And also, what is these things are known. I'm putting a different way. I think is nice, but they are known in some way. When does causal data science comes into play? I would like to try to answer that. And there is a computer science trick here. I would like to parameterize now these tasks in terms of the 4 dimensions that you discussed. The populations are not the same, the sampling, the quasi-experimental condition, and so on. Let me just do it here. It's parameterized. Let me pick one here just to try to parse. The causal inference from observation study. We are talking about the same population, D1 here. Now we have a change in regime. We are going from observational to the experimental, from OBS to the DUX. We have in some way the same sampling conditions, and so on. The same variables that we are trying to make the claim that is before. And that's the task that we discussed now in terms of these 4 components that I just said. Now, question, just paraphrasing what the lady asked in the top here of the previous slide, do these dimensions exhaust all possible data collection modes? Not really. There are many other types of combinations. I just copied, by the way, the previous one, the last one that is the interesting one. Let's give the credit for who the credit is due. Now there's different type of task here. What I like to call experimental inference or generalized instrumental variable. This is by Philip and C.O. Wright. The type of inference that we're trying to do is like, we have the regime that we are collecting data from the do-Z, and we are trying to make a statement about the do-X world. Under what conditions can we do that? In some way, if you open up the theory, it was hard-coded to do from OBS to the do-X. And we are still moving across the regime's dimensions. It's totally possible. Again, you collect data on diet, that is Z, and you like to make the effect on cholesterol level, that is X. Again, this is due to my reading of history. Philip and C.O. Wright, some kind of special contest in linear and so on, but it opened up the possibility that this exists in the world. What about dimension 3? There are issues also. There is acknowledged. Maybe you have the data set. Everything is constant in the other dimensions, but dimension 3, that you have selective pressure on age, as I described. Maybe you have an overrepresentation of older people in this particular population. Is this possible? You can make this statement. This is, in other words, there's a mismatch here between these dimensions. Now, how can you get the effect of the whole population, given that you have the data skewed towards the older people? Again, I'm not the first one talking about this problem, maybe in this way, but not the first one. Turns out there's a professor called James Heckman, University of Chicago. He got the Nobel Prize around 2001, if my memory is not wrong, for partly this work showing that there is a possibility of recovering when the data is messed up in this way in the left, and you can make a statement as in the right. Special setting and so on, but very cute, just to allow us to know it is possible. And there's a boom of work trying to generalize these results. Last one here of the list, transportability is also called external validity, that is related to the task number 1. The maybe you collect data happens very frequently on bonobos, and you are trying to make our cousin, and we are trying to make a statement on Homo sapiens about us. Under what how on earth can you use data from this guy to make this statement? Under what kind of assumptions, under what kind of conditions? How do I write that in some language? And then I can play computer science. I can write an algorithm that will operate on top of this. They also have been acknowledged, very semi-formal, but anyhow, this is the quasi-experimental book, if you are in the science, by Shad. This is one of the Bibles, the Shadis, Cook, and Campbell, in the Concept of Psychology in 1976. Now my comment here will be, the special case of these dimensions have been addressed in the literature, mostly in isolation, and very special variable or special parametric conditions. In practice, they appear together, what I like to call causal data science. In other words, each data set, as I said, is a tuple in this space, and we also have it can be a collection of these guys, and we are trying to make a statement in some kind of particular domain star. It's called pi star under these conditions. I would like to spend a little bit of time now just to make it more concrete, to unpacking what could be this task of the first time of the transportability. Maybe you have data from New York City, and you are trying to make a statement about Boston. How can you do that given that those are not the same population or type of people? Then I'll talk about transportability, extrapolation, robustness of causal claims. The first problem statement here is also I like to call robustness. By the way, just to repeat here. First about robust, how the thing will go and maybe hold in this other setting that is the target environment. Let me read the research problem here, the research statement. Is it possible to compute the effect of a treatment or drug X on the outcome variable Y in a target environment pi star where no experiments can be conducted using data experimental findings from a different environment pi? Now I have the figure of this dimension 1 here starting getting a little bit more syntactic. We have pi and pi star. We have data of experiments in pi, and you are trying to make an experimental claim in pi star without being able to conduct the experiment. 0 data points in pi star. How can you do that, or is it possible to do it? Sometimes it's possible. Our goal will be trying to understand when and how this is the case. Let me give an example here for concreteness. Again, what experiments in New York can tell us about Boston. The pi population here, the source population is New York. The target population pi star is Boston. And now I have some type of causal graph here. I would like to recall the semantics of the causal graph first. Causal, and I'll go fast here. Maybe I spend 1 week that in class, but bear with me, I'll do it in 30 seconds. But it's okay. Each arrow in this graph, in reality, is a representation of what's going on in the space of this structural causal model, is the space of causal mechanisms. Then if you have an arrow here from X to Y, it means that in this underlying system, the Y is equal to f of Y of X and something else, possibly. Or Y is a function together of Z as well. And Y equal to f of Y of X, Z, comma, UI, let's say. And the same here with the X. X is equal to the f of X of Z and UX. Now this is a standard graph. That's good. Everyone is at the same page. Now I would like to introduce argumentation here because we are talking about domains pi and pi star. Then we are not talking about one SCM, structural causal model. We are talking about model in pi and model in pi star. Then we need to overlap these guys in some way. How do you do that? Now you have different type of assumption about the invariances that are going on between pi and pi star. And as I think many people here that I know and familiar with graphical models, the assumptions are not in the arrow in reality. Assumptions in the graphical models are in the missing arrows. In the basic one, in the very basic object of BaseNet, the assumptions, missing arrows mean condition independence. Here, missing arrows means something 10 times stronger, which is good for some sense, but bad in others, but that is functional invariance. Now, whenever you don't have this yellow arrow here that I call S arrow, the selection arrow, this is called a selection diagram. Whenever you don't have an arrow, it means that you are making a claim about the invariance of this underlying mechanism. Then there is an invariance here between the function of Y. This means that the f of Y is equal to the f of Y star. But there, in other words, yellow not here, but there is yellow pointing to Z, which means that we are making no assumption. It could be that f of Z is equal, but you don't know, then we'll put f of Z is possibly different than f of Z star. And f of X is possibly different than the f of X star. Then this is a model imposing constraints over the space of the SCMs. And this is qualitative. Now we also have input, that this is part of the input of the TR problem, transportability, I call TR. Now another part of the input is a quantitative. We have a distribution in the source in pi domain, New York, that you are able to collect X, Y, Z, and you are able to collect the Y given to X, comma, Z. The effect of X and Y for each age group. And in Boston, the last piece of input here that is also a data set, you have our distribution in this case. This is the P star of X given Y, X, Y, Z in Boston. Side note here is not fundamental, but it turns out that this difference in the mechanism, whatever migration happened, whatever culture between New York and Boston, this different f of Z, these will pop up in the data. Then you have the P star of Z will be different than the P of Z. The age distribution will be shifted, for example. Not entering in Y, just this is implied by this assumption, or the lack of assumption that they're the same. Now, this is part of the input, qualitative plus 2 quantitative. And what is our goal here? Our output, or the target of this thing, the analysis, is that we would like to compute the effect of X and Y in Boston, given that we don't have data here. Can you leverage the knowledge that we have about the relationship between Boston and New York, plus these experiments in New York, and a little bit of observational distribution, some type of information, non-causal, that we have in Boston, in order to answer the causal question in Boston? And this is a prototypical TR, transportability problem. It turns out that in this particular instance, the answer is a decision problem. The answer is yes. And it turns out that this is a simple combination here about we just get the z-specific effect of X and Y that we have in New York, and we weight that by the distribution of the new age distribution that we have in Boston. In some way, we're accounting for this difference in age here. Interesting enough, it doesn't matter that how they are seeking drugs, New York versus Boston, is different. Still, this doesn't show up here. It doesn't matter. We needed to account for the difference in the ages, but not about how people are getting treatment. This is a well-known formula. This is known as the transportability formula. Some people like to call this the recalibration. I dislike it extremely because it's an overloaded expression. We are asking about the existence of some function from the distributions that we have to the target distribution or quantity that we want to kill. Here the question is like where this endeavor started, by the way. And the question here is about is this like a physical law, like a Schrödinger type of equation, but for the data sciences? That no matter what is X, Y, Z, no matter the relationship between these guys, nothing else matters. I can always plug in these numbers in the right side of this equation, and I will always be able to get the effect in the left. In other words, is this a universal law? Sounds kind of a little bit too crazy. Probably no. I would like to show that this is not obviously not the case. Transport formula depends on the assumptions, or what is going on in these underlying SCMs or the relationship between them. I just copied the one from the previous slide. I added this by the triangle, Z, X, and Y. I added these bidirected arrows and dashed. This just means that there is unobserved confounding that is affecting X and Z. There is unobserved confounding affecting X and Y that is shared. The U shares in the underlying mechanism. I will leave it the details, but if these guys are not there, everything in some sense will be trivial. What makes this really hard is these unobserved variables. But anyhow, they are there. There is an assumption here in this model that there is no bidirected between Z. The assumption is here in reality. There is no bidirected between Z and Y, which means that the source of exogenous variation of Z is not correlated or not covariant with the sources of variation of Y. This is not our assumption here, the bidirected. The assumption is here, not here. But anyhow, if you run the analysis, this is just the data sets that we have from the previous slide. If you run the analysis, we get the same formula, the same reweighting by the age distribution. Our question, is this universal? And the answer is like, I don't know, let's see. The note here that maybe someone messed up and we don't measure the age, as you mentioned in the previous example. I may have forgotten to say, but this is age, this is the treatment, and this is the outcome. Someone measure a proxy for age. This may be the language skill of the person. And it turns out that there is disparity of the language skill. It's a function of age. Age keeps growing. The skill is monotonic, probabilistic in some sense. But there is the disparity between how kids are getting education between New York and Boston. Now, question. Can we, let's say that the numbers are the same. You do the proper discretization. The numbers are the same as in the data set that we have in case A. Can you apply this formula here in case B, in which now age is unmeasured, and you just have this proxy Z? The answer is no, not true. In reality, if you do that, you can be going despite of the size of the data set, you get further and further. The right way to do is get just the copy, the effect Y do X from the source. And note here that the disparity is not even related to the X and Y, this disparity here. And the do X will cut this guy here too. And anyhow, that's the transport formula in this case. In other words, the first baby example, this I think first appeared in 2011, and is first example showing it is not universal. People have been taking this formula as being universal for a long time. In reality, since England, 200 years ago, but I will defer history for this next. Or the, what about, this is everything Z comes before X and Y. What about the post-treatment or post-decision? If you have X, a drug, Z is a biomarker, and the biomarker move for whatever level, and in turn will affect the Y. Can you combine the data set in this way? Should you get just the marginal effect in this way, or what is the right way of doing? Turns out to be neither. There is a different way of combining these two data sets with the same numbers such that you can get the effect in Boston. Then the lesson here, the lesson here is like causal assumptions are required since the data doesn't impose enough constraints over the causal structure. And the results of the analysis are structure sensitive. In other words, this data set that is part of the input does not allow us to distinguish these three guys. There are more, by the way, I'm just showing three. And each of them, we already saw, is a completely different way of being combined, or how you combine them in order to get the query. Then no way out. There's nothing that we can do. We need to elicit knowledge in this form or equivalent form to this one, this type of assumptions. And anyhow, this is a first result, first observation, I'd say. In reality, operating, I would like to take one step back. Now, I will take different steps back. But the first step back, this is a decision problem, computer science like, is the target effect transportable? Yes or no? We'll start with a triplet. The triplet contains a target query, a causal model, and a data collection. The query that we operated so far was the P star of Y given to X. Now we have a model that is kind of overlap of these two causal models in the pi and pi star that has this yellow. And you have a data collection that have these heterogeneous data sets with selection, confounding, and different kinds of bias and heterogeneity. Now, our goal here as the computer science or the statisticians answer the question. Based on the current knowledge about the problem that is encoded in the model, and the available data sets that are encoded downstairs there, is the research question that is one, P star Y do X, answerable, I call transportable, but computable from that. Then, again, our goal is to have this inference engine that we eventually take this triplet and say yes or no. If the answer is yes, it means that we have this kind of mapping that from the observational data, in this case, in the target, experimental data in the source, these will map to whatever you want there in the target. And that's the general idea, or the problem that we're studying, I should say. The kind of results that you have, I'll go relatively fast, but the kinds of results that you have is a syntactic characterization for the decision version of the transportability problem that's essentially asking for some type of reduction of this expression P star of Y given to X to I'll not fully read here, but for expression in terms of the input distribution, which is quite natural, one of the sides of the implication. To show the other that is some kind of necessity is a harder problem because there are many distributions. I'll show in 1 second. But then you have this query, you do some, I'll not go the algebra here, but you do some kind of massaging. Usually you're expressed in terms of this indicator here that is the switch between the source and the target. I write it, I find the expression without, in terms of the input distributions. In other words, there is no S here in some way. And this is good. This is what we want. Just notice that there is a W here that in some way is allowing us to isolate the S from the Y. This will be important. I will come back to that in 1 second. But in other words, we have an if and only if symbolic type of condition or characterization for the transportability problem in the sense that I described. This picture is good for people in theory, maybe. Some kind of model theoretic interpretation or semantics for transportability. Think that we have this space, it is called omega space of all possible causal mechanisms in the world. Don't observe that. Now we'll decide to put some constraints over that this is compatible with these particular graphs. And then we'll put another constraint there that there is some kind of distributions, these models here, each point here is a SCM. They can induce our input distribution, PV, P star of V, PV do X. Those are the distributions that we have as input of the problem. Now, what we have is like in the intersection of these guys, for all SCMs here, they generate the same P star of Y given to X. Then you say it is transportable. I don't care about which one was the guy that generated these distributions. I don't care, because they all agree with the same query, with the query. They generate the same distribution. Then let me just read it here. Formally, for any two causal models or collection of mechanisms encoding this unobserved nature, I call nature 1 and nature 2, and 1 and then 2, such that they share the same structure. They share, parsing roughly here, they induce the same distributions. In other words, the distribution in the, I don't know, the distribution in the source, P of V given to X in the first nature is equal to the P of V given to X in the second nature. The P star, the distribution in Boston, generating by the first model is the same as the distribution in Boston generating the second model. Now, if this happens, if it's transportable, it means that they also would agree with the P star of Y given to X for all 2 and 1 and 2. And that's the model. Anyhow, it's a model theoretic. Computer scientists tend to like this one, and I like the interpretation. I'll contrast that 1 second for you, because sometimes this doesn't happen. Why we care about that? Because this is not a given. Assume that someone messed up, and they didn't measure the variable W here. Then the graph focus here. The graph here will be this one. Same system, same collection of mechanisms, but now we are marginalizing out the W variable. Now the question is like, is the quantity transportable? And the answer is no, or no power. What this means that there are these 2 unobserved natures, not parsing here for the sake of time, in which they have the same graph, they will generate the input distributions and disagree in the target distribution. In other words, in our picture here in the model theoretic, the intersection here between these spaces, there are some SCMs that generate one due distribution and some other SCMs that generate another due distribution. Which means that this level we cannot commit because I don't know which one is the true one. And that's the idea of transportability. Now, second result, this is symbolic characterization. Second result is algorithmic characterization. We have algorithms that decide if the effect is efficiently, if the effect is transportable. We essentially input the guy on the left, that is this, of any size, essentially the causal input. This is not, it takes as input, and then the algorithm will return what you need to measure in the source and the target. Source is the guy in green, and the pink is the one in the target domain, that everything is non-experimental here. Just an example of the kind of result that you can get. In reality, I'm showing you baby examples. This is a real problem that we have been working that is more usually is more involved than that. And anyhow, that's the reality. And result of what we're trying to get. This is like some kind of automated way of doing this transportability analysis in a larger settings. This is related to some type of lung disease. It's a medical setting. If you want to try that, suggestion here, subscribe, usually academic email, causalfusion.net is a tool that you have that allows people to play this game. This is the case that we have, the classic one. You can play, input the graph and get the formula, and even there is a button that you can do the derivation into calculus or in counterfactuals or so on. So it turns out to be quite useful to people to understand what's happened. This is the other graph with the proxy that we see there, that is just the P of Y given to X and so on. Take a look. It's still beta, by the way. It's closed at the university. As I said, university email are usually approving everyone. There are thousands of users using this tool at the moment, trying to learn causality. Let me skip this one just for the sake of time. Now I would like to conclude doing some type of, you take a little bit, but some type of, this is kind of classic. I would like to say where we are in this, our goal of doing this causal inference engine. This I call a field report because this is my way of thinking about that, what we have been doing on the field. We're starting from the first task that I described, that is the one, the classic causality in which we have this triplet. The target is observational, the causal model. This is one way you could write that in terms of ignorability statements that you want. And then you have the PV as the input. And then we kind of have maybe a 30 years endeavor about how to solve this problem, how to write the assumptions, and so on. I think now we'll crack that. This was my task 0. I started from there maybe 20 slides ago. Now I would like to broaden that. We also discussed a little bit today about the strict conditions that we have. One is I call environmental conditions, that is the transportability that we just discussed. I couldn't talk much about Heckman's kind of dimension, that is the sampling dimension, and we also have the experimental dimensions of right. This is all about the data collections and give these different tasks, 1, 2, 3. In some way, this is accounted for here. The task is the same, P star of Y do X. We have a causal model, but now related to the data collection, you can have this confounding bias, selection bias, and transportability bias in the data collection, everything mixed together. Then we do have general results starting. This is just a summary of in 16 or for the 5 years before. We have very general results about this particular version or general versions of this problem. Now I'd like to just give another problem that based on, I know some people, I think they could be interested. One of them is about policy interventions. I think it's I call task number 4. I just give you the gist of the task. What does it mean? Instead of the do that we usually have, in practice, it's very hard to implement this hard type of intervention that you shift all the mass to a particular event. Do x is equal to 1 means 100% x is equal to 1. Usually you have some type of probabilistic version of that there. Then we call this a soft intervention. I personally call the sigma intervention, that is the name that you gave. Now, you do have a general way, a general condition to do a yes or no for when we have this type of setting. And we also have something that is, I'm very happy with that, something called the sigma calculus, that is the first symbolic calculus for reasoning about policy interventions. It's anyhow a generalization of the do calculus. There is also algorithms, but this allows us to understand a lot about what's happening there. Another comment, this is very related if you guys are interested. I didn't mention today, but for off-policy evaluation in reinforcement learning setting. Hey, RL, we have usually policy type of interventions that is not do. How can you do off policy and move across these different regimes and different types of agents? Then check it out. I'll be happy to talk maybe in the future here also about the CRL. Check crl.causal.ai. The whole world that I'm not talking today, I think is very interesting about the marriage between causal inference and reinforcement learning for decision making. These are some references there. Now, another problem, happy to talk more about any of the problems that I'm not talking here. Another types of causal inference that you like that generalize or deviate from what the canonical is this the data-driven version of the problem. So far we assume, again, the do X there, the other is there, I'm keeping these two, but we do assume that we have one particular causal model, that there is some causal analyst or some data science, a real person that is understanding and is able to write this thing down. In practice, that's one of the bottlenecks when you talk with real people doing the analysis in the other buildings in some way. Then here what in the department for the computer sciences, it is a computer science note. Now, what we do here is instead of assuming that we have the graph, now we can try to learn what we call the equivalence class of graphs. There's a literature on structural learning, and now I no longer have one single graph, but I have sometimes exponentially many graphs here. Usually you will not list that because the space is huge, but it's some kind of regular expression of way of expressing, of encoding the assumptions related from the data collection. Now we also need to upgrade the engine to take these guys into account. And this is what we have, starting from this. This may be UI, maybe a best paper, or a best student paper, I should say. Starting doing this work, let's upgrade the engine to take into account this different type of object in the causal model dimension. Again, we can do the yes or no. This is the first, another no, this is first causal inference. There's a type pipeline that is entirely data-driven and is also complete for non-parametric identification. In other words, you don't need to touch entirely in addition to some basic assumptions about faithfulness, or strong assumptions about faithfulness and some type of minimality, or Occam's razor like of assumption. Another task is about estimation. I put that under the rug in some way, but it's a very good problem. Assume that we have, this is the setting that we got, assume that you run the analysis and we get a yes answer here. In reality, we don't have the p's that are lying on the left side, left bottom, but we have finite samples from these data sets. I just picked one. Now the question, like how on earth, Victor is here, has amazing results of the DML that we are fun about the double robustness and the biasness. How can you estimate from finite samples this quantity? Now, the idea is how to do estimation and to have some type of, try to plug in the literature or modern literature or machine learning to try to scale up these inferences from the finite samples perspective. This is some works, this maybe a few hundred or even thousands of papers trying to do with a specific, this task, with a specific causal model known as the backdoor model or ignorability model. This is the first type of papers trying to do with any possible model. It turns out to be a hard problem, but now we can do it as well. Very happy, and thank you, Victor, for inviting also. It's very happy to be here. Now, it's a very cool problem. Moving on here, I'm almost done. Counterfactuals, I talk about a layer 2 effect of interventions. There are more complicated type of, or more refined, I should say, type of questions that are not the do questions and are not soft do questions. That is the sigma. There are things called counterfactuals. This is layer 3, or level 3 in Pearl's hierarchy. Sometimes you have the question about the X prime, the guy took the drug, Y prime, the guy is dead. Now you ask, would he be alive? That is the Y, that is the opposite of Y prime, had he not taken the drug. That is the X, that is the opposite of X prime. It's high level cognition, very important for AI. Now we have a way of handling some type of nested counterfactuals and so on. Happy is a very recent result, and happy to talk about that. Almost done. Now my second last, the neural. This is very new. This is happening also now. There's a lot of excitement about doing neural nets papers. I couldn't see a paper that is doing causal inference with neural nets that I appreciated. Then we wrote one. It's important. Our goal was to leverage the power of neural nets. They are kind of very impressive when you're trying to do computer vision and reinforcement learning. I would say that part of the success and the excitement about modern machine learning, at least in the last 10 years, is about the power of neural nets. Now the question is like some of the inferences that we have in causality, they are very robust and nice, and we have guarantees, but in terms of scalability, for many variables, it may not work when you're doing the estimation. Can you try to leverage the neural nets in order to do that? Then that's, we can have some kind of hybrid between the neural and causal. Happy with the paper is also recent with my two students, Kevin and Kaizan, and also contribution with Yoshua Benjo at the Mila. Happy to have it. And now we can do that. You can do a yes or no answer from inside the neural net. Then I say it's the first time in the world that a neural net is able to perform causal reasoning. In other words, it takes causal assumptions and is able to say if you can get causal conclusions. Not the identification itself, not only the estimation, for any type of model. Happy to talk also, it takes some time to understand, but happy to talk offline. My last one here, the approximation. So far, we are very strict and brittle in some way, if you wish, with this yes or no answer, because it's a little bit computer science mindset. Sometimes have shades of gray. And in particular, this kind of flexibility is somewhat important if you get a no answer. Because yes, we can start trying to do ML, you can do DML, or you can use neural nets, and there are challenges, but yeah, now everyone is happy when you get a yes answer. But what about if you get a no answer, you say what to the guy on the other building? Bye-bye, do your research, and we cannot say anything. Then we start that. This was even a few years my NSF career, how to do approximate causal inference. By the way, inspired by the theory community, TCS, that have similar tension maybe 30 years ago or so, when they, in the P versus NP type of problem. Start having approximate algorithms. This is like my kind of, in honor of them, we are trying to do this here in our way. Then instead, a no answer means that we don't know anything about the effect of between the target quantity. We don't know where it is between that. Then it's hard to say there's a positive effect, there's a zero effect, or is it a negative effect. Should I approve the drug? Now, what we'll do is approximation. Let's try to bound that in some way. There's a complexity involved with that. It's a few papers, but still pretty much open problem. How to bound that for any causal model in a way that you can make at least help the guy that's making the decision on the other side. Then anyhow, that's the problems. Some topics I didn't talk here today. I talked earlier with students. Apparently there's a lot of interest in fairness. Also, there's some results that I couldn't talk, and so on, and reinforcement learning. But let me move on. I will not do this one just for the sake of time. I will just say postdoc available too. If someone is here and graduating, I will be happy to talk. And I'm trying to recruit and get a bright postdoc that wants to help to pursue this agenda. Conclusions. Causal data science, to me, what we are aiming for, the program is a principal framework for combining substantive knowledge about the phenomena under investigation with data to generate two things. One, causal explanations. Two, robust and generalizable decision-making. My bias here today was more about the first, about how to explain why things happen in the way that they happen and how things work, but you can also use that for decision-making. Important insight, I'll follow from this observation, simple but impactful, that is not all data is created equal. Most modern data collections are messy and plagued with systematic bias that need to be understood first. I also don't want to code first. This is more experience. Everyone is optimizing or coding. They don't even understand what's the bias and what they are trying to control, with catastrophic side effects, by the way. Anyhow, digression here. With systematic bias that need to be understood and controlled such that causal claims can be made and maybe decision-making as well. Decisions can be made properly. Causal data science provides tools to solve long-standing problems in the empirical sciences that now people call data science, including confounding bias, selection bias, measurement error, generalizability, and fusion. Thank you for the attention. This is also thank you for both the Causal AI lab in the left, that is, I'm highlighting here the people that I talked about the work, and also the collaborators in the right. I will be happy to take questions. Thanks.
Thanks. So we have time for a quick
Am I in the right room here? Or it's like
Is there anything left to do?
Oh, that's a good one, Victor. I think so, a lot. The question by Victor is like, is there anything else to do? And I said, yes, there's a lot to do. But I do think that it's important to have some structure about where we are. And my bias here is about presenting the results that are somewhat more polished and kind of nice, but many things are open. More towards the end of the task that I was giving, like the very last one, like the approximations and bounding. It's very recent that we can bound some cases when it's discrete, and some types, in general, some general models, but discrete case. Continuous, for example, we don't know how to do well. But I can go task by task and tell you where we are and what is not good in reality. There is, yeah. One thing that we talk, just one example also, that we talk, or maybe in Twitter too, is about these graphs are great, but and the equivalence class is great too, but those are very too extreme kind of settings. One, the graph that is purely based on knowledge, and people is able to elicit and do any possible. In reality, the graph is knowledge encoded about all pairs. You get all pairs of VI, VJ over the endogenous set, and the graph is encoding knowledge about who judge statements about all pairs. And the equivalence class is something that is totally data-driven. Those are two extremes of a spectrum. But the point is like, we're spending a few years now and we don't have a result yet, I would say. But how to touch in the middle and have some type of combination, a model that allows us to have background knowledge, plus it's coming from the data, another piece. It's a hard problem. And I think it would be cool. Maybe someone can help. Or another thing I would say, I forgot to say that I don't have many collaborators, no collaborator in MIT so far. Then this is a collaborator. If you guys are interested in the topic, I will be happy to talk as well. It's kind of unusual. There's people from good places and I will be happy to talk with you. But many questions are still open, I would say. But you do know a lot as well. I would like to make this a statement. It's not unstructured and everything goes and as.
Could you explain a little bit more about neuro-causal thing that you mentioned?
Yes, yeah, that's a good one. But just before the previous one, also we are working on that, but maybe your cyclic models is one that is really, I don't take as a criticism of the theory, it's just more excitement for us that we have worked for more 1 year or two. How to handle cycles is non-trivial, right? You can unfold, right? This is the textbook kind of answer. Let's unfold and let's sample in some kind of nice frequency and everything will be acyclic. But in practice and from our experience in econometrics, there is more to be said and more refinements that maybe could be done. And how to combine these with these type of advances in graph-based or graph theory-based, it's like unclear at the moment. Happy to talk more about that. But to your question now about the neural models, yeah, the idea, I would say, there is this result in neural nets that got me going, starting maybe 2019, and I'm out of that. This reality about the universal, old result of you can approximate any function. That is a universal approximator. Now, given that that's true and basic fact, and if you see the definition of SCM, I don't have a, SCM is nothing more than, I could write, but it's nothing more than a bunch of functions. Now the question for us is about why then before that, and we got this feeling, people in AI and ML, that any problem, any task can be reduced as the input and output. Then you have, there is a universal approximator. Anything in the world can be reduced as an input and output kind of problem. And you see the definition of causal model, structural causal model, is this tuple that is types of variables, and then you have two things, right? Functions and a collection of mechanisms, and the P of U, the exogenous kind of distribution. But now, if you have function and I have someone that is a universal approximator, why can't I just get this universal approximator and use that to learn the SCM? Then you understand the question, right? Guys, do you understand the question? It seems, in other words, the starting point is like, it seems that what we're doing in causality is easy, or there's no problem in reality, because I have a powerful tool to learn any function. And the causal model in its deepest form is the SCM. I just noticed that I have the dryers here. They are hiding from me. Right? Just 1 second, just to draw the picture. But you have this guy is nothing more than a pair, F and P of U. This is the SCM star, that is the true one. Now I have a box, and this guy, I have a box here that is the universal approximator here. And neural net is just one example, but let's say that is the case. Now, and this guy outputs some stuff. There is some kind of distribution here. Why can't I get this guy, give as input for this, my universal approximator thing, and I'll get output here that is the M, let's call the M prime, or NN. This is a collection of functions that was learned from this guy. Now, why this object is different, and this guy also could have the F and the P of U, the F and N. Let me put a star here, that will be easier. There's the F here, and the P of U here. Now, why this guy? Let's ignore the noise for 1 second. Even the more extreme case, deterministic or so. Why this F will not be the same as my F star?
Is the problem identifiable even?
Yeah, you need to define what is identifiability here in some sense. But you want to add? I didn't hear you before. But
No, I mean, it's already feels a lot far-fetched because the application where everything I'm thinking of just one sample, and then so I don't even have an idea of what the structural model is. So like,
no, but entertain the idea at least for 1 second. Allow me to okay, SCM is generating PV. Let me just add a bit then to be precise. And then you have this DV. A data set is true that you don't have access to this guy. This object is also an abstraction. But now, let's say that this guy is really huge. And I understand that your case maybe you have even less, but this is huge guy. Now, why cannot get this object input to this box, and I can learn a collection of functions that describe this distribution over these observables V? You could. Now you get some kind of collection F here. Now the question is like, why this F is different than the F star? Yes.
you might have partial observability.
Speak a little bit louder.
Yeah, you might have partial observability.
And what do you mean by partial observability?
Well, the unobserved counters that you might be learning spurious correlations.
Yeah, but even if I tell you that, let me fully define here because I'm being, in reality it's a tuple with 4 components. V, U, this is the observables, this is the unobservables, this is the mechanisms, the functions, and this is some kind of probability distribution. Now, here, this guy, let's say that you have this fellow that is also over the same set V, the U, I need to put a prime here. Yeah. Now, in some way, you have the same set of observable variables in both sides. But I think what we alluded, I will avoid the mystery here because I don't know how much time you have. And this is like, can have also talk for 1 hour about this result. But the idea is like, is a very limited way to think about that the SCM is just PV. Because this is just one angle or one way of interacting with this complex object. as we know, or at least some people, but this object in reality entails different types of distributions. One is the PV given to x, for example, as we discussed. For all x in V, an exponential number of distributions that is entailed by this object. And also, this guy also entails a different distribution that is the PV. We can write in different ways, but I write a star, but in reality, this one example is like the PV, PY, X prime, Y prime, for example. This is a counterfactual distribution. This is an interventional distribution. This is an observational distribution. Then this complex object, M star, induces qualitatively different distributions. By the name that we go to this one here is called the ladder. I call the PCH, the pro-causal hierarchy. This is a data structure with these different distributions. Now, if I just observe a piece or the data, or even the piece of this object, okay, I can reconstruct, for sure I can reconstruct again, or I can use anything to reconstruct this aspect of this guy eventually. It's very finicky. You can spend 1 month trying to make the thing to work, but eventually you'll be able to make it work. But still, just having access to this piece of data tells me nothing about this guy, and also even less about this particular layer 3. This is layer 2. This is layer 1. This is layer 3. There's nothing about layer 2 or layer 1. Then the whole idea of the paper, this is this paper from NeurIPS 2021, is about to say that this is very naive reading. Universal approximability is kind of orthogonal to what we're trying to do that. There is this idea, it's almost like not all data is created equal. There's these different types of data sets. And if I just have access to one piece, maybe I cannot get any statement about the other. Suggestion of the theorem about that, you can have a measured theoretical kind of interpretation of that. Check my website, sorry, the R60. This comes as a causal hierarchy theorem, the CHT, that we cannot make a statement about these other distributions without the lower, from higher level distributions with the lower level distributions. Now, if you know this result, now you're already sensible to say just, you need to add something, and this is what we do in the paper, some type of inductive bias to the learning process of this neural net, or using this UA, could be any, such that maybe this guy will be a good proxy to the M star. And now which kind of proxies are good or not good? It's a very good question. I'll pick it offline or we'll continue. But thank you guys, thanks, I appreciate it. I have a